course, thanks again to Rajat, Siva, and Frank for this great opportunity. It's my second time. I had the honor to be present also 2 years ago at this beautiful event. I really look forward for the next one, wherever it will be. And let me also thank the entire Indian community. For me, it's a privilege to be here. Was so productive and fun last time that I decided to come with my family this year. We were traveling through Karnataka for 2 weeks, really beautiful place and beautiful community here in India. Sundar Zaga. Today, my plan is to talk about Node2vec, or, okay, I recall it triangle-biased random walk. That's actually linked to what Nelly, where is Nelly? I don't see her. Sorry. What Nelly mentioned along the way. So she mentioned Node2vec, which is an algorithm. It's a very popular algorithm in network science, I understand, for graph embedding purposes and for many other purposes. And my goal is not to talk about this algorithm, but about the brickstone that is behind this algorithm, that is the Node2vec random walk. In fact, I'm a random walk lover, more from the pure side. And let me tell you that this is joint work, very fresh. So this is joint with Gianmarco Bet, who is my colleague in Florence, and then 2 Dutch colleagues, Lars Schröder and Clara Steeghaus. Now, how did I get involved in this business? Well, Lars is doing the PhD currently under the supervision of Clara Steeghaus and Gianmarco Bet. They're both based in Twente, Lars and Clara. Gianmarco is in Florence. And Clara is someone much more applied than I am. He likes really network applied problem with a solid math background. So in fact, I didn't know about this Node2vec problem. She mentioned me this project, this framework. And in fact, last year, Lars visited us in Florence. They were doing the supervision of this PhD with Gianmarco. Then they spoke with me and I was interested. I found fascinating this random walk model that is nothing but a random walk that is biased when it is along some triangle, as I will make precise now. So let me define the random walk I'm interested in. I find it a very cute model, except that it's a nasty model in the full parametric regime. Let's see that. So what it is, Node2vec random walk? Let me give you a formal definition, perhaps with a picture we understand much better. It's simple. So Node2vec, and my goal was to start, I proposed them to start answering very basic question about a random walk, how we study simple random walk on graphs. So let's see what we can say in general, very elementary about this random walk. So this is, you are given a graph, given a graph G, vertex set, edge set, and I will assume that the graph is undirected, and this is a delicate assumption. I mean, most of what I will say will no longer be true if the graph is undirected, if it's directed. Undirected, connected, and simple. And simple, I mean simply there are no multiple edges or self-loop. But these two assumptions are easily, you can weaken it. I mean, all I will say is more general than connected and simple. So you have a given graph, undirected, connected, and simple, and are given 3 parameters. And alpha, beta, gamma parameters. Okay, so what is it? This Node2vec random walk is not a Markov random, it's not a Markovian random walk on the graph, but it's rather a second order Markov chain associated to the graph. So let me define it. Given a graph, Node2vec is, you can consider it in discrete or continuous time. I will consider it in discrete time. Is a stochastic process, is, if you like, a random walk. X, I will denote it by X. Discrete time is actually a second order chain X with the following transition. So let me write down the transition for every UVS. The probability, its second order chain simply means this is not Markov in the sense that conditionally independent is not only from the present, the future, but you need to prescribe present and one step in the past. So if my present is time n, for every n, x time, you will be at position n plus 1 in the vertex u, given that you were at the present location in V, and that one step in the past you were at the starting, if you like, vertex S. This probability is proportional to one of these three parameters. So alpha I will do it with a picture. Hold on a moment. Bear with me. So let's say we have a graph. These are the vertices. Let's say it looks like that, for example. I don't know, there are continuations. So this is a local part of a graph, whatever graph you like. So let's say that at time n, you are here at the vertex V, is at time n, and you came previous time, at time n minus 1, you were at this vertex here. So to define this type of second order Markov chain, you have to describe the first two steps. So the initial point, one more point. So in a sense, you are prescribing an initial measure on the directed edges of the graph. Then when you look at this object, so what is the evolution? So let's say you started from here, you did one step. What is the next step? So this is the transition mechanism, and you go with probability proportional to alpha if you want to do a backtracking step. You want to go back to where you came from. So this is the rate to go back to where you were coming from, a backtracking step. So this alpha, so let's say in this picture, I said this is starting u, if u is equal to S, right? Then you have probability beta and gamma, and that's make the nasty part of this object, depending whether your edge where you're coming from is part of a triangle or not. So in this case, I did on purpose this picture, because you see here, I have the possibility to go from vertex V to this vertex U. This belongs to a triangle. So you do this move with probability proportional to this beta. While this type of move, there's no edge between S and U, so it's an open wedge, if you like. So you're not part of a triangle, and you do this type of moves with probability gamma then proportional to gamma. That's the mechanism, the full parametric description of this second order Markov chain. Clear?
I don't understand, because this is not rates, this is the discrete probability, so things must sum up to 1.
Yeah. I mean, the point is it's proportional to this. You have to normalize it depending on the local degree of V. Now, I'm not writing on purpose this because it depends on the local neighborhood, and that's the answer. Does this answer your question? Good. So this is the second order Markov chain.
I don't look here. I don't understand the definition of the gamma steps. So what's?
Sorry, I didn't finish to formally diagram. So beta, if you like, U and S belong to the edge set of the graph, and gamma as So all other cases, provided, of course, you reach a reachable point from V, if these 2 points are not connected by a direct edge, you are in an open wedge, if you like, and then you move like a simple random walk move with probability gamma. Now, what can we say of this object? A few observations. First of all, when alpha is equal to beta and is equal to gamma, this is nothing but our best friend, simple random walk on the graph. Now, when beta is equal to gamma, so you're not biasing triangle move, you really see it as a standard moves. This is a very interesting object that there's been much attention in recent years. If alpha is equal to 0, what is this model? This is the very well-known non-backtracking random walk. Non-backtracking.
Graphs are always finite.
No, I'll come to that when stating the results. My goal was really to understand in terms of the graph structure, when is ergodicity kicks in, when it kicks in for this graph, when this process is well defined. What can you say?
You will have some bounded degree assumptions then.
Depends on the results. I will come to the results later. Now I'm simply explaining what this model is and which this generalizes a number of well-known processes. So if alpha is equal to 0, this is the well-known non-backtracking random walk. Simply, you have no possibility of going back from where you are. This is an object that has been studied now in recent years, but pretty much for different reasons. Arenco has a nice work in which they improved with Fitzner a few years back, I guess 2012, the diffusivity and CLT, functional CLT for this object on ZD. So these objects are nice or not, depending on also which geometry you study. And this is quite technical with the lace expansion techniques and so on. Then there has been lots of other results. I mean, 2006, Alon, Sly, Lubetzky, they realized that this walk has the same invariant measure as the random walk on finite graphs, namely as the simple random walk, namely the degree bias distribution, though it makes faster the non-backtracking random walk. Okay, and there are a number of other results. I cannot list all of them for this non-backtracking that is becoming more and more popular. It's related also with deep question in terms of spectral quantities. Lots of people now, Scharsbordenave, they are exploring spectrally the structure of this non-backtracking walk. Still, when beta is equal to gamma and alpha is positive, this object, this Node2vec, is what I will call alpha backtracking. And this was the non-backtracking, alpha backtracking. And this other variant of this object, still it's pretty similar to some extent, depending on the question, to the non-backtracking companion. In fact, in these three cases, what is the invariant measure on finite graphs? The invariant measure we know of this object, and is nothing but the degree bias distribution. So there is provided a good irreducibility assumption on your finite graphs, the probability of being at V will be proportional to the degree of V, okay, normalized with the size of with the sum of the total degree. Okay, let me point out a little thing. Why this invariant measure is true for these three models? Well, for simple random walk, simply because it's a reversible process, satisfy the detailed balance condition on undirected graph. You can easily check, I mean, we do it in first course Markov chain, this reversibility, satisfy that. Why for these two objects, it's the same that on finite graph, the invariant measure is still the degree bias distribution. This is for a different reason. And the reason is that you can lift to edge space this second order Markov chain. It will become a Markov chain. And you realize that on this lifted space, these objects are bistochastics. And that's why you can reduce the problem of studying this alpha backtracking, non-backtracking to a counting problem in edge space. When you consider this Node2vec fully when beta is different to gamma, all this beautiful simplification disappear. In fact, let me now, before entering the results, how am I doing the time? Let me quickly explain edge lifting of this object, because the edge lifting, so this is a second order, is not Markov, it's second order on the vertex space. Now, let me explain, even when beta is different from gamma, the full Node2vec, you can edge lifting. So it's a non-Markov object, but we like Markov theory. We've been developing Markov theory for a long time. So what we can do, X on this non-Markov, this second order, X on G, you can lift it to new process, X, Markov, really, Markov chain, on a new graph. That is graph where the state space is simply the space of directed edges now, and the edge set of this new graph is the space of wedges, directed wedges. Okay, that's what I call this object W. So now, how do you do this lifting? Well, this is intrinsically, you already see from the initial measure that that's the right space to see this object and to unveil the Markov representation that you can use Markov theory. So this process X is nothing but now Markov chain that for every direct edge, now for simplification, for notation purpose, directed edge, I will point out E1 is starting vertex and E2 is head vertex. So for every E and E prime in this space of directed edges, you have this Markov representation. You can represent this, what it is. This is nothing but the path measure associated to the original process that after 3 steps, you are in E2, given that, but more generally, yes, for every time n, A2, you go from E to E prime, yes, this is E, this is E prime, right, so I need to, you go from here to there, xn is equal to E prime 1, equal to, or the endpoint of E, and xn minus 1 is equal to E1. So this is formally the definition of this Markov chain on the space of directed edges, and you immediately realize that you don't distinguish. So in this process,
Luca, this is all second order then.
Huh?
This is all second order?
What do you mean no second order? This was this second order chain. Now I represented on the space of directed edge as one step transition matrix to go from
n minus 1. Something wrong.
I don't get the question, sorry.
So the process where you take n minus 1, both is Markov. So that's x.
Yeah, so this is truly the second order Markov chain. What I'm defining here is a Markov chain X bar on this space with transition matrix, a stochastic matrix that is defined this way, from a directed edge E to directed edge E prime. Is that clear? Thanks. Okay, now when it comes to this full parametric model, this Markov representation can be useful for some results, but perhaps not for all results in understanding really the basic questions, because you don't distinguish at this level between beta and gamma statistics. So the beta and gamma statistics is, well, but at least in these 3 cases, when beta is equal to gamma, this stochastic matrix become bistochastics. So let me point out this very quickly. So this Markov chain now, X, is bistochastic if and only if beta is equal to gamma. So namely, if you don't see the different triangle, non-triangle moves. but you only play with the backtracking parametric or not. By stochasticity, well, easy to check. So every Markov chain, we know it's a stochastic matrix that sums up to 1 for each row. By stochasticity is the opposite, namely that sum up to 1 over when summed over columns. So for every E prime, you want to check that if you sum over all edges, this transition kernel, this indeed sum up to 1. And this, if beta is equal to gamma, that's very simple. Actually, due to time, good exercise for students, just draw it and you check immediately that, well, all the sorts of edges, incoming edges, you will see that you will only see when E is equal to minus E prime. That's the only move where you have to play to pay alpha divided by the normalization. And then all the other possible E that enter this E prime, then they only have the same probability 1 over the degree minus 1 times gamma. So you will check immediately that this is bistochastic. Therefore, for a bistochastic Markov chain in general, the invariant measure is on the finite graph is the uniform measure. So this Markov chain X has its invariant measure, which is uniform. 1 over cardinality of the direct edge. And now, out of this, you can go back on the original process just by what is called a pullback operation. Namely, if this Markov chain has an invariant measure like that, then you can conclude in particular that this Markov chain, the original one, then X admits a limiting measure, limiting measure, pi of V, which is nothing but the pullback of this pi directed from the edge space. So namely, the sum over all edges in the directed edge space whose ending point, so E2 equal to V, of this pi hat of E. Now, if you count down this turns to be simply the degree bias distribution. So this is true if and only if beta is equal to gamma. Now, goal is what can we say when beta is different to gamma on this object? And in fact, so this alpha backtracking case and the non-backtracking has been studied by a number of people, Masuda and Mang in 2011. They figured out that also for this alpha backtracking, there's this degree bias distribution. And actually, some Indian colleagues, Barot, Shankar Bahamidian, Souvik Dara, in 2021, they studied this Node2vec algorithm for community detection purposes. In their case, they call it Node2vec, but they then restrict only in this case beta is equal to gamma. Because really this object, when beta is different from gamma, starts to become really nasty. So what is it known when beta is different from gamma? As far as I know, there's only one little result that is due to Clara and Lars, who last year, so really when beta is different from gamma now, what can we say on this object? Well, Clara and Lars showed last year they characterized the invariant measure, but on a very special geometry, that is the invariant measure on household model, household with cliques. Okay, I see that I'm doing bad with timing, so let me mention in words, in a sense, the household is a graph. You start with a graph, whatever finite graph. Every vertex has degree, say, k. you replace this vertex with a click of size k. Okay, so it's a model with implanted clicks, if you like. And then on that specific geometry, because it's contractable in an easy way, they could really characterize the invariant measure. And this is the only geometry in which you can couple this object to a non-backtracking random walk, or if you like, to an alpha backtracking random walk. That's why they could characterize the invariant measure on this very special geometry. Now, yep. I don't know what a random intersection graph. Delegate, but we have now I have a characterization on this geometry. In fact, I guess due to time, I have till let me start discussing our results, new results. Before saying so, let me give a second Markovian representation for this object. Because as I said, edge lifting, it's a very useful representation. Still, if you really want to study this object with beta different from gamma, you better start to think on a wedge lifting. Let me now describe a second Markov useful representation for this object. Everything under control? Yeah, I see. Okay. So we do one more step. So this Markov chain, this second order Markov chain, you can look it up in this edge space, but notice you cannot distinguish the thing here unless you say where these edges are in the wedge decomposition. Now, wedge space is nothing but a sequence of, right? So wedges of this type. Let me also denote such that SU, let me call it the first part of the wedge, and UV, second part of the wedge, such that these two things belong to the directed edge set. So it's this space, the space really of concatenable. So when you look together, two concatenable directed edges. And this space, you can decompose it uniquely into wedges of three types. Wedges belonging to triangles, disjoint union with wedges of open type, as in the picture, and then with the flat edges that are these edges here that you can backtrack, okay? So this is a useful representation. Now, on this space, why not to consider a second Markov chain, X bar, now on G2, which is nothing but a space where now its vertex set is the wedge space. And then, okay, edge set is the corresponding sets of how these wedges would concatenate with each other. Now, on this space, you can immediately distinguish the type. You have the type of which sort of wedges there are. So this is wedge type. And notice that since the underlying graph, I was assuming was undirected, now wedge type do not change whether I see one wedge in one direction or the other. So this is the minus W. And this is just this alpha parameter if the wedge was a flat one, or the beta if the wedge is really inside a triangle, or the gamma transition if it's an open wedge. Now, on this space, I can define a new Markov chain in which I can concatenate wedges, and the probability to go from one wedge to another is proportional to the arrival W prime. I see this. I cannot cross this line. I moved there. wedge Markov chain. So P hat W prime is nothing but this is function. This is the wedge W. This is another wedge W prime. Yes. If, okay, I called the second edge of a wedge W2 and W1 the first part. So if W2 it's equal to W prime 1, so you have the characteristic function telling you whether you can concatenate these two wedges, and then this probability is nothing but probability proportional to this edge type, lambda of W, normalized with properly, so that this is a probability measure. And in particular, so what is relevant here in this wedge representation is the in neighbor and the out neighbor of a wedge. So let me draw this, and then I state the results. 15 minutes. Results are very subtle. Let's see. Okay, so let me define here also the in neighbor of a wedge. This is nothing but all the possible W's that I can concatenate with W prime. So this means simply all the possible W's such that its second point is equal to, and then there's the out neighbor of a wedge. The out neighbor, so if you like, this is the in neighbor. All sorts of wedges of this type, which include, you see, all possible wedges, and including the one that goes back here. So if you like, this one, the flat one. On the other extreme, the out neighbor of the wedge, well, let me describe it with a picture. So this is W prime. So the out neighbor are those wedges who has the first starting edge. 2 and 1 is the, so if you have a wedge, this is 2 is the second edge. So this is omega prime 2, and this is omega prime 1. It's just the components, the directed edge component of these two. The first, they have a direction, so the first, the head, the tape. Yes, the out neighbor is nothing but the set of wedges who has the first starting edge. So wedge, edge. So for instance, and it includes W prime as well. So for instance, this is in the neighbors, but also this one. Of course, the one that can get reversed. So this one as well. Okay, so this is the out neighbor. Sorry for not being formal, but I see time is running and I think you're grasping the concept. Now, right. Okay, and now you may try to hope for bistochasticity of this other Markov representation to try to see whether there is some counting possible to reduce it to a counting problem. Forget it. You can check it, and it comes a very awful condition of bistochasticity that the graph should be extremely artificial with the right symmetries and the right multiplicity of alpha, beta, and gamma. Pointless. That's not the right thing. So still, this representation is very useful, and now I think I can state with the time I have at least the statement of the 3 main results we proved. So first result, theorem 1, it's what I would call Node2vec ergodic theorem. Node2vec ergodic theorem. Why am I calling this way? Because that's essentially the analogous of the Markov chain ergodic theorem. So how do we intend the Markov chain ergodic theorem? Simply structural minimal assumption on the underlying graph to guarantee that your walker, your simple random walk, forget the initial position, stabilize, and in fact, so ergodic theorem, I could phrase it this way. Now, it's very delicate, another point, that this Node2vec in the full parametric regime, its property changed drastically whether alpha is equal to 0 or not. In a sense, alpha equal to 0 is drastically more rigid. It's more directed, the space. So unfortunately, we don't have yet, in these years, lots of people I'm working with, and I see many of we are trying to expand the electrical network interpretation of random walk in directed setting, but we still don't have a general theory of electrical network as we have it for reversible Markov chain on undirected setting. We still don't have all this beautiful theory in directed setting. Partially, we have it. So, and that's why alpha equal to 0 or not drastically change the picture. Anyhow, theorem one, I could phrase it the way, first, if alpha is bigger than 0, so that means you have the possibility really to backtracking every time, then this wedge Markov chain is irreducible as soon as the graph is undirected, connected, and simple. And if G contains at least one triangle, is also aperiodic. So you can really, this Markov chain forgets its past and stabilize. While if alpha is equal to 0, already the irreducibility, you need to have some assumption, as Rajat was pointing out before. For example, you need that d mean is bigger or equal than 2. Otherwise, this process gets stuck in a point and you have absorbing states. But you also need more. You need that d max is bigger than 2, because you don't want that it ends up in a ring, cycling in a ring. And this is only for the irreducibility. So already this implies this Markov chain to be irreducible. Then for a periodicity, we don't have very neat condition as far, or better, we have it. That means if you want to guarantee for alpha equal to 0 that this is aperiodic, you need to have at least 2 cycles of this whose length as greatest common divisor 1. This cycle will allow you to lose the periodicity constraint. So in this case, you can guarantee that the process will forget its past, will stabilize, and in particular, its invariant measure has a nice structure in terms, if G is finite, then you will converge to a unique invariant measure, which can be, it's proportional to this weight, PW, times all possible W prime that you can concatenate with W. So in the neighbor of W. So this is the general structure of the invariant measure of this object on the wedge space. You can phrase similar results in the directed edge space, but you don't have such a nice recursion concatenation. This you see it only easily, quickly in this wedge representation. And okay, and then in particular, it exists a unique limiting measure. So really the original second order Markov chain will converge to that for any starting configuration. And you can characterize this in terms of the pullback. Now, 5 minutes. We have other 2 theorems, so I guess I have to explain it inwards. Well, theorem 2, let me still, can I write here? No. Was the non-crossing area? I can write here. Theorem 2. When is this object becoming really simple? On the irregular graphs. On the irregular graphs, all of a sudden, big simplification comes in, and we spent some time, it's not obvious, but you do have the following things. Let G be finite. then this wedge Markov chain representation of this Node2vec in the full parametric regime satisfies a Eulerianity, weighted Eulerianity, if you like, an in-out ohms balance condition, if you think in terms of electrical network, satisfy Eulerianity that is of this form, that is related with this in and out neighbor. So Eulerianity meaning sum for all W sum over W in the, for all W prime, let me write it, okay. For all W, if the sum over the one that can be that are in the out neighbor of W, if this global weight is equal to the in weight, so the sum over all the W prime in the in neighbor of W, only under this Eulerianity condition, so P satisfies this Eulerianity condition if and only if G is deregular, in which case the invariant measure is explicit and it's simply proportional to this weight, lambda W, to its weight. And in particular, if you pull back to the original space, the invariant measure is nothing but the sum over the wedges that ends up, so wedges of the type whatever, ending with the last point in V. And this is not at all the degree bias distribution. It's not proportional to the degree of V. It's simply, what is it? It depends on the locally, the deregular graph, how it looks like. Now, in this deregular case, it satisfies the Eulerianity, if and only if it's deregular, this wedge Markov chain. On top, it satisfies a directed detailed balance condition, which is not equivalent to Eulerianity. And we have counterexamples. As a last result, I have to close, so I will not discuss it, but let me mention, please.
The lambda in your sum should be prime.
Right, sorry, yeah. This you mean? Yep, correct, sorry. I have no time, I would draw a nice picture, but yeah, I think you understand from here, no? So the in and out balance in the starting edge. And in this case, it is regular, we can characterize everything, and it satisfies directed detailed balance condition in wedge space, which is not equivalent to this Eulerianity. As a last result, in fact, by adapting a proof of Hermon that used for the alpha backtracking, a bit more complicated, we have other assumption on the directed flow in this whatever graph you consider. If it's the directed detailed balance condition is satisfied, then we can even prove on infinite graph that this object is recurrent if and only if simple random walk is recurrent. In particular, that's the case on the triangular infinite lattice, for example. And I think these are three general results that really are cracking the very basic fundamental structure of this type of random walk. And now, given this representation, we have tools to, okay, we are finishing this work. Actually, I finished it with collaborators on March 30 before coming here. Tomorrow or the day after should appear on archive. You may look at it, but I see that now we can really crack all sorts of other questions gradually. For instance, you can ask, diffusivity on certain graphs and so on, because at least now we clarified what are the basic structure depending on alpha being 0 or not. And saying that, thank you all for the attention. I can stop here.
Questions? Shine.
I'm just curious about any other possible explicit examples. Like the deregular one is a nice one.
Yeah.
But then suppose you have the, say, the 2 grid, and you kind of flip a coin to choose whether the diagonal inside each box will stay or not, right? So that's like a periodic structure.
Yeah, yeah. So
Yeah, does that work for something nice?
what do you want to prove? Do you want to characterize the invariant measure? No, the Eulerianity is if and only if is deregular. Then we have other tools that now I didn't have time to discuss, the directed detailed balance condition. And we really see that in the edge space and in the wedge space, these two directed detailed balance, you can characterize the invariant measure, but they're not equivalent. And in fact, we have examples, very tricky counterexamples. So for example, if you have a click and you remove only one edge, you will see that this directed edge wedge balance condition is satisfied, this Eulerianity not, but if alpha is equal to 0, is not satisfied the directed edge balance condition. So it's really heavily dependent on the details of these things. But in principle, I mean, this is the generic form of the invariant measure that, and we can relate it also to the invariant measure on directed edge space, and it's delicate the way they. But certainly there are these tiling infinite, like I was looking actually question for you, because physicists have these useimetry sort of lattices that are tunable lattices in which you can, they are not deregular, but you can tune what sort of cycles you want locally. I was interested to finding periodic easy graph to be described to really characterize explicitly the statistics. So if any of you has this familiar with this sort of models, I would be interested to.
Any quick questions? Himashish, can you?
On a ring. You want to generalize the Node2vec to have biases on cycles more of longer length than a triangle?
Yeah.
Of course you can. It will become even worse. I mean, Hermann studied alphabet tracking and k-bet tracking. Depends also on the question. You want to study recurrence, then that is not that difficult. But you need to have assumptions to do that. And these are questions related with the directed flow. You want to study invariant measure locally, more delicate question. Ergodicity, more delicate. So, of course, you can come with all the possible higher order generalization and analyze them. Yes.
Okay, and in view of time and coffee, let's thank Luca again.